Welcome to a lesson with Dr. Powell. Let's look at a technique called partial fraction decomposition, which is used to simplify what we're integrating, the integrand, what's in here, if we have a fraction of polynomials. Let's look at an example where we have something like x squared plus 1 over x minus 1 quantity cubed. Now, in order to think about this technique, we're going to think about some ideas that'll help motivate us. First, when we write down a number in base 10, that's what we usually do here, like 231, we can think of this as 2 times 10 squared plus 3 times 10 plus 1 times 10 to the 0. So we have coefficients here. These coefficients are less than 10. And then we have powers of 10. It's kind of like a polynomial where x is replacing 10 or something like that. Okay, so numbers have unique base 10 expansions, but they also have unique base 2 expansions. For instance, the number 7 can be written as 1 times 2 squared plus 1 times 2 plus 1. It's powers of 2, and this is unique. So, and in using digits, we have the 1, 1, and 1. So in base 2, actually 1, 1, 1 is the same thing as 7. So we have these kind of unique representations. Likewise, let's kind of come back here and let's go back to this fraction of polynomials that we're looking at, that we're going to try to integrate. Partial fraction decomposition is useful with fractions of polynomials. How does these base expansions help us over here? Well, with polynomials, you can do the same thing. Base expansions, you can do things relative to maybe like in base x minus 1, say. Notice we have a cubed here. So let's look at the numerator. We can actually think of the numerator written in base x minus 1 powers. So it's going to be have different, so like x minus 1 to the 0 is just 1. Then you have x minus 1. Then you have x minus 1 squared. And that's as far as you need to go because this x squared, right, and squaring. So that's kind of the highest degree that we need here for this expansion when we rewrite this in its base x minus 1 expansion. Now, another thing is the coefficients need to, now before we were thinking they had to be less than 10, but in this case, they just have to have degree less than whatever this is. So this degree is, this is a polynomial. X minus 1 is a polynomial of degree 1. So x minus 1 itself is a polynomial of degree 1. So that means the coefficients have to have degree less than 1, which means they have to have degree 0, meaning that they're going to be constants. So you have a constant number here, A, B, and C. So that means that this numerator actually can be represented like this, where these coefficients are just numbers. So let's do that for a minute. And we don't know what those numbers are yet, but that's part of the process. We're going to figure out what they are. So if we take this and we divide this whole thing by x minus 1 cubed, so we're dividing by x minus 1 cubed, which is the same thing as multiplying by 1 over x minus 1 cubed, and multiplication distributes over addition, hence this division also distributes over the addition. There, distributes. So it goes to each part. So distributing it over here, this square and this cubed, we could reduce that fraction, so it's just a over x minus 1. Plus, now over here, this x minus 1 to the first and cubed, that reduces to x minus 1 squared on the bottom with a b on the top. And over here, it's just c over x minus 1 quantity cubed. Now, these right here, if we were integrating just this, or just this, or just this, that's a whole lot easier than trying to tackle an integration like this. because you can use a u substitution here, make u equal to that. And since like c times u to the -3, just a backwards power rule, and the integration wouldn't be too bad. So that's the technique. We can take something like this and we can change it into something that's more workable. Now we can actually even just take a rule here, perhaps say that if especially if this degree right here is less than this degree, then we can rewrite this top in the following way: for some coefficient a over x minus 1 plus some b constant over this plus c constant over that. We're just looking at different powers, x minus 1 going up from 1 to 3, and that would work. We could just take that as a rule, that we can always do that, where this guy right here, see these constants always have degree less than the first denominator to the right here. So just the factor that we're raising power. So not 2, but just that. So then we know that they're constants because they have degree less than x minus 1 itself. Okay, so, well, in this particular example, let's actually work out what a, b, and c are in this case. Okay, so again, so we have x squared plus 1 over x minus 1 cubed, and we want to find the general antiderivative of that. And currently we know we have something like a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 quantity cubed. Okay, so so this is really what we're integrating at the moment, but we don't know what these a, b, and c are. We got to figure out what those are. We do know, though, that, let's just kind of erase this for now and not think about integrating quite yet. Let's figure out what those constants are. We know we have equality right here. This is equal to this. And this is a nice equality because it's an equality of functions. Like this function is the same as this one. I mean, they're the same, right? Meaning that any value of x that you plug in will still maintain this equality, because this is true for different values of x. So we can just start plugging in different things for x, in fact, and we get 3 different equations. If we were to plug in, for instance, 2, why is 2 nice? 2, and don't be too nice, but why do we, no, but why do we plug in 2? Because 2 minus 1 is 1, and so that would look like a plus b plus c by plugging in 2 on this side, and on this side you would have 2 squared plus 1 is 5 all over 1, so just 5. We have one relationship between a, b, and c just by plugging in different values of x. So at x equals 2, we have an equation. We can come up with another equation by plugging in something else. We could plug in, let's see, we could plug in 0. 0 might be a nice one. So if we plug in 0 on this side, we have 1 over -3. So just, or I mean -1 cubed is what I meant. So 1 over -1 cubed, which is just -1 on that side. And on this side, if you plug in 0, you have -a squared, so it's positive b, and then that's cubed, negative cubed, which should be -c. So we have 2 equations and 3 unknowns. We can come up with another equation here by plugging something else in. Let's see, we could plug in in fact, yeah, let's get another one. Let's see, let's do 3 be okay, so that would give you a 2. I mean, it would be okay. I mean, maybe we could do that, or we could do a half. People are okay with fractions. We could just do 3. That's fine. Okay, so if we do a over, so that would be a over 2. This would be, because it's because we're plugging in x equals 3. This is that x equals 0. Okay. So we have a over 2 plus b over 4 plus c over 8. And that's going to be equal to 3 squared is 9 plus 1 is 10, all over 2 cubed. So 10 over 8. So we have 10 over 8, which is the same thing as 5/4. So we have 3 equations, 3 unknowns. And we could work through the process of figuring out A, B, and C are from these 3 different equations. You can add equations together to kind of simplify things. In fact, notice that if you add these first 2 equations together, what happens? You add these 2 equations together, these a's cancel, these c's cancel, you're left with 5 minus 1 is 4, so 4 is equal to 2b. So that means that b is going to be equal to 2. Okay, so we know this is 2. All right, now, and then we could replace 2 everywhere right here. So we got 2, 2, and 2. Okay. All right. Now, actually, with that, knowing that, we could maybe work with, let's see here, with both of these. Let's see here. If we subtract, okay, now, yeah, so if we subtract 2 over here, we're going to get 3 is equal to a plus c. In fact, that's equivalent to doing it in this equation too. Subtract 2 over, you get -3 is equal to that, multiplied by -1, it's the same thing. 3 is equal to a plus c, and it better be the same thing in those, in that particular cases, if we want this to actually work. So 3 is equal to a plus c. Okay, so we know that. And then we have something over here. Maybe we could multiply this whole equation by 8 to make it look a little simpler on the bottom. So multiplying this by 8 would be like 2 times 5, which would be 10. This would give you a 4a. This would give you a 4. That's just a half times 8, so 4, and then plus c. Okay, and then we can subtract the 4 over, so we have 6 is equal to 4a plus c. Now we could subtract this equation from this equation, so the c's would cancel, and we get 4a minus a is 3a, and over here we get 6 minus 3, which is 3, meaning that a is 1. So this a is just 1. Now let's figure out what c is. Okay, now we know, well, right here, if a is 1, c better be 2. So, all right, and we can verify, let's see, so 1 and 2 and 2 is 5. Okay, and -1 and -2, so -3 plus, yep. Okay, that works. And then we have 1 and 2, so a half plus a half is 1 plus, so 1 plus a fourth, yep, definitely that. So I just double checked to make sure that these were the correct values by plugging back in. So this right here, we do a little bit of algebra, but we get this. Okay, so then we just go ahead and we can integrate this now. All right. Okay. So we have 1, 2, and 2. X minus 1, x minus 1 squared, x minus 1 cubed. All right. So plus and plus. And now we're going to integrate this, so we can kind of think of integrals just one at a time, individually, separately here. This one, the integral is going to be the natural log, and you can check this, natural log of absolute value of x minus 1. Take the derivative of natural log, you're going to get that. Now we do this so that we maintain the same domain here as this, because if we didn't have the absolute values, we would have a different domain from derivative to antiderivative. We wouldn't want that. So this is one way of doing it. Actually, there's more ways of doing it, but this is the standard way of writing it down, I suppose. So that's just what we're gonna keep doing. All right, so then over here, you have 2 divided by x minus 1 squared. You could think you do a little u substitution, but u substitution is easy because the derivative of this u is just 1. So we'd end up getting, and so we could just think of this as 2 over u squared and just take an antiderivative of 2 times u to the negative 2. So that would be 2 u to the negative 1 over negative 1. So which would be negative 2. And then u to the negative 1, I guess we could just write, oh, okay, yeah, so that's fine. I guess we could just make a plus, and then we could write, or we could do it various ways. I'll just do it this way. Negative 2 over x minus 1, because x minus 1 is u, right there. Okay, so we got that, and then do a similar procedure over here. And so this is 2u to the negative 3. And the antiderivative, we have u to the negative 2, but then you divide by negative 2, and you have a 2 there. Those 2's cancel. So it looks like you just have plus minus 1 over x minus 1 quantity squared. Okay, so then this right here would be the antiderivative, the general antiderivative. We put a plus c there, and we've just taken the integral of what we had originally, and we first did some partial fraction decomposition using the fact that we could split it up to constants over these successive powers. So constant, because the constant was 1 degree less than the x minus 1 that we were raising to these powers, we went up, and we go up this far, and that has to do with the with how we could rewrite the numerator as an expansion, since it had with its particular degree. But in general, what we do is we just automatically just go from 1 up to that power. So 1, 2, 3, and then we just put down things that are constants. We might get more or less than we need, but that's the standard procedure, at least in this technique. Thanks for watching.